Hey, good morning, guys. So mm, I had two requests about midterm regrading, but I won't do any regrading because it's just 6% of the course, and I don't want to spend my time and your time on these minor adjustments. So this so today is the last day when we actually will do any math. Beginning from next week, we will use the built-in libraries that do everything for us, and gradient descent and derivative calculations. So today is the last, maybe tough class. Yes, but after that, you can bury your math for maybe entire life and use just built-in libraries. Yes?
I'm just kind of wondering if does this have to do with the formulas that are used for later like the later algorithms that we're going to learn, or is it like just a
No, today we actually will derive the formulas that the built-in libraries run under the hood. So we will build the manually, but then you will use like gradient descent. We wrote our code, then we used built-in inside scikit-learn. So the same is here. We will write the code for neural network today manually, but from next week we will use the built-in libraries. Okay, so yeah, let's continue our discussion how um, our derivative computations work in different packages. So we created the computational graph to evaluate our function based on inputs x1, x2, x3. And now we want to calculate the derivatives of the last node with respect to inputs. So the first mode is called forward. In forward mode, we calculate uh, for example, derivative of the first layer, derivative of x1 with respect to x1. What is the derivative of x1 with respect to x1? Huh? Yeah, you can just say with that.
like you design a diagram and then when you're deriving, you go backwards.
So the first mode forward, yeah, the second will be backward. Yes. So to calculate the derivative of our f with respect to x1, from this formula, we can see that it uses the derivatives with respect to x1 from previous nodes, from inputs, from x8 and x3. So that's why we first will calculate the derivatives of the previous nodes with respect to x1, and then we will get the final derivative. So what is the derivative of x1 by x1? 1. What is the derivative of x1 with respect to x2? What is the derivative of x1 with respect to x2, for example? Oh, sorry, let's do x2 with now we take derivatives only with respect to x1. For example, x2 with respect to x1. X2 doesn't depend on x1. So what is the value? 0, 0. Okay, so we know how to calculate the derivatives, and the same will be x3 with respect to x1. So we know how to calculate the derivatives from the first layer with respect to x1. Its zeros unless we take the derivative with respect to itself. Then let's calculate derivatives of x4 and x5 with respect to x1. So x4, what is the function there? Multiplication. There is multiplication of x1 and x2. So what will be the derivative of x1 times x2 with respect to x1? The derivative of the product, yep.
Should be x2.
Yes, it will be x2, correct. What is the derivative of x5 with respect to x1? x5 is sine of x3. So I can write like detailed formula. It will be x5 with respect to x3 times x3 with respect to x1. But the derivative of x3 with respect to x1 is 0. So because it doesn't depend on x1, it's all derivative. Now we'll calculate the derivatives from next layer, and when we have okay, finally we will reach the f. So then derivative of x6 with respect to x1. The input into variable x6 was x4, and it was exponent. So the derivative of exponent, it will be the same exponent of x4 times the derivative of x4 with respect to x1. But derivative of x4 with respect to x1 we calculated on the previous step. So what will be the derivative of x7? x7 has two inputs, x5 and x4, and its product. So the derivative of x7 with respect to x1 will be first derivative with respect to x4 and derivative of the product x5 times x4 with respect to x4 will give us x5. So every time when we know the only inputs in our node, we have the rule. Just we have a lookup table how to calculate the derivative of the product, for example. So, and derivative of the product is the, for example, x4 times x5 with respect to x4 times x4 with respect to x1 plus x4 times derivative of x5 with respect to x1. So it's just the table derivative, and these derivatives we calculated on the previous. So now we should calculate the derivative of x8 with respect to x1, and then we can use our formula for derivative of x9 with respect to x1, which uses x8 and x3. So derivative of x8, the derivative of x8 was the sum, the sum of x7 and x6. Derivative of the sum is the sum of derivatives, so it will be just x6 with respect to x1 plus x7 with respect to x1, which we calculated on previous. And finally, what is the derivative of this division? So we divide x3 by x8. Or no, we divide x8 by x3. So Let's see. The derivative with respect to denominator, derivative of 1 over x is negative 1 over x squared. So the first derivative will be negative x8 over x3 squared. And the derivative of the numerator x8 over x3, it will be just 1 over x3. Again, when we know the function, and this function is the division, we know how to calculate the derivative. Okay, and these derivatives we take from previous steps. So this is called forward mode. And let's look at the time complexity of these calculations. So what is the time complexity to calculate our function? Let's say we have n the number of nodes in our computational graph. So how many steps should we perform to evaluate our function if we have n nodes in our graph? Yes, you can just speak up.
I'm just,
Or of n, yes, because in every node we do maybe maximum 2 operations, for example, addition, or maybe evaluate the calculation of the function. So the total number of operations will be O of n. What is the time complexity to calculate the gradient? What is the time complexity to compute the derivative with respect to x1? Again, in every node, we will do about 2 operations, like in case of addition. So what will be the time complexity to calculate the derivative with respect to x1? Yes.
I would say n because we have.
Both, yes, also both.
Calculate each derivative for each node.
Yeah, each node we use maybe 2 times, maybe, yes. So all of that. But we want to calculate derivatives with respect to x1, to x2, to x3. This is the vector. So what will be the time complexity to calculate all the derivatives if we have the input size d? It will be O of n times d. And if the input size is, for example, 100 features, or image 1000 times 1000 features, okay, so this will be your time complexity. So now we will look at another mode backwards, which will return us O of n time complexity for evaluation of the gradient. Okay, so backward mode. And also sometimes people call it backpropagation. So So we begin again. Now we will begin with ends. So we want to calculate the derivative of our function with respect to x1. Instead, we will calculate the derivative of our node x9 only with respect to inputs in this node. So in this case, with respect to x3 and x8. Oh, x9, yep, with respect to x3. And because x9 is x8 over x3, it will be negative x8 over x3 squared. And derivative of x9 with respect to x8. So we will calculate derivatives only with respect to inputs. Then we will move to the upper last node and take the derivative of x8 with respect to inputs, with respect to x6 and x7. And because x8 was the addition, we know how to calculate these derivatives. So x8 with respect to x6 will be 1, because x8 is addition, x6 plus x1. And derivative of x6, x8 with respect to x7 will be also 1. Because x8 was just the sum of x6 plus x7. There was addition. Okay, then we move to the previous node, x6. It has only one input, x4, and this exponent. So derivative of x6 with respect to x4. And derivative of exponent is exponent, so it will be just x6. X7 has two inputs, so derivative of x7, and this is multiplication with respect to x4. Because it's a product x4 times x5, it will be x5. And the derivative with respect to x5 will be x4. Okay, then we have x4 and x5. X4 is the multiplication, so it will be similar. It will be, so x4 has inputs of x1 and x2. And x5 has one input, x3. The derivative of the sign is cosine. Again, every time we know the function in the node, and we know the exact rule for the derivative of this function. So it's just a lookup table for the sum, for the functions, and so on. With respect to x3, it will be a cosine of x3. And finally, yeah, we have also this first node. Okay, so if I want to calculate the derivative of our function with respect to x1, we look at the inputs in our node. And so the inputs in our node are x3 and x8. So we take the derivative. Let me change it a little bit back. So we will use again exactly the same chain rule, but to evaluate the derivative of x3 with respect to x1, we will also use chain rule. Okay, actually x3 is the terminal node. For example, x8 with respect to x1. We will look at the inputs into x8, which are x6 and x7. So to calculate this derivative, we can use again chain rule, which is which will be the sum. The sum x8 with respect to x6 times x6 with respect to x1 plus x8 with respect to x7 times x7 with respect to x1. So the idea here is that I will use the derivative of x8 with respect to its inputs. I don't know. Do I need to? I can write this explicitly. So x8 times x6 with respect to x1 plus x8 with respect to x7 times x7 with respect to x1. Then to calculate the derivative of x6, we look at the inputs in x6. There is one input x4, so it will be x6 with respect to x4 times x4 with respect to x1. So again, we will perform n operations. But the only difference will be in these terminal nodes. If we take derivatives with respect to x1 or with respect to x2 or with respect to x3. So in other words, except the last multiple in this derivative, we don't we will reuse these derivatives. Only the last derivative will be different depending on x1, x2, or x3. Does it make sense? So it means that we will calculate the gradient of the derivatives in all of n operations. So this is called the backward mode. And of course, this mode is used in automatic differentiation packages. There is also cross mode, which is the combination of forward and backward modes, but I'm not sure if it's used. Maybe in some packages it's used. Okay, so now let's yep.
So the main difference is that instead of just going iterating backwards while calculating derivatives, you just create a lookup table and then do substitutions for x1 and x2, x3 in this case.
Well, the difference is that in forward mode we calculate the derivatives with respect to x1 on every step. In the backward we calculate the derivatives with respect to previous nodes. And the only difference will be on the last layer, because only on the first layer we will use for x1 or derivative with respect to x2. So all the other derivatives we can reuse for calculation of the derivative.
It will always calculate, so if I wanted to get a derivative in forwards mode, for every node that I go to x4, x5, I always have to take them with respect to x1. In that case?
Yes, and forward we will, as you remember, we to calculate, let's say x6 with respect to x1, we used the chain rule x6 with respect to x4 times x4 with respect to x1. In backward mode, we don't multiply by x4 with respect to x1.
Just use a substitution. We just use a substitution.
We multiply only on the last step, where it's an odd value, and it will be either x4 with respect to x1 or x4 with respect to x2. And because x4 depends on x1, it will be x4 with respect to x1 times x1 with respect to x2, which is 0.
So it just produce, so in backwards mode, it just produces a lookup table, and all the substitutions are done at the end.
Yes. So actually the formula is absolutely the same in forward and backward mode, but we just calculate more clever the derivatives. So instead of just multiplying by derivative of x8 with respect to x1, we multiply by the nested derivatives from the inputs into our current. Yes.
Is there any reason why you would ever use forward mode outside of for teaching purposes? Or backwards mode?
Yeah, so when I believe it was in Middle Ages when this algorithm was introduced, people realized that they can calculate derivatives more efficiently, and they call this backpropagation. But it's nothing else than the chain rule, but applied in explicit form. Yes, so yeah, people before mid-80s, people not only use this for teaching purposes, but they use this for also calculation of derivatives and neural networks. And this was a great breakthrough to calculate in a more efficient way. So, okay, now let's apply this to our neural networks. A little bit more math. So, this is the visualization of our multi-layer perceptron. So we have inputs. Input is a batch of data where data are in the rows of this matrix X. And the dimension I denoted by dx, the number of features. N is the number of input points. I hope you remember how we calculate the hidden layer is the product of matrix with weights times our x vector plus bias. So as the result, we will have exactly the same number of points in hidden vector, also n points, but the dimension will be different, which we denote by dh. So in other words, our matrix has shape dh times dx. And b, what is the shape of b? Dx or dh? Exactly the same as h. dh has the shape of h. So after that, we apply nonlinearity. For now, we use just sigmoid function. And we get the A vector, which is just sigmoid of H, pointwise. And because it's pointwise, the shape of this matrix will be exactly the same as the shape of matrix H. And after that, we apply the second layer, or in other words, just another matrix multiplication, matrix times A, to get the output. And if the output is one-dimensional, the shape of this matrix was 1 times dh. And as the result, we get for every input point, 1 output. And the number of outputs is also n. Now let's apply backward algorithm for calculation of the derivatives. You remember we should calculate the derivatives with respect to v2, w2, v1, w1. These are our parameters that we want to tune, to update. Who knows how to make these slides to fit the screen? I don't know. Okay, so and finally we calculate the loss function, which is the average of the errors, for example, for MSE loss. So you remember in backward mode, we first calculate the gradient of our last node with respect to inputs. Because the input into our loss function is O, we will calculate the derivative with respect to O. So derivative with respect to O will be just 2 times the difference. So this is the first derivative in backward mode, the derivative of loss function with respect to inputs. And this is how it looks in code. So in the forward mode, we calculate this loss function. So it's, I don't know why I didn't use NP-min. I used NP-sum and divided by n. The sum of squared differences between inputs. So here, x denotes the input into our layer, not the inputs into our model. X minus y squared, and also the gradient. The gradient will be 2 times x minus y. So all without indices represent the entire column entirely. So this is component-wise, this is the vector representation. Derivative with respect to all endpoints. Okay, next layer is activation. After all, we have activation. Oh, no, sorry. After all, we have also linear layer W2 times A. So, and the inputs in our O layer are A's. So we should take a derivative with respect to the inputs A. If you look at the expression for our output, what is the derivative with respect to, for example, the first point and component A1? It will be W11. With respect to the last point, it will be W1. So the derivative with respect to the first line of this table will be the first line of matrix W. the derivative with respect to all these numbers will be the second line. So the derivative of our loss function with respect to just one number from this matrix of A's will be multiplication by the weight from our matrix W W2. Okay, so this is the vector notation. The derivative with respect to O times the derivative of O with respect to A, and the derivative of O with respect to A will be just our matrix. Then we want to calculate the derivative of our loss function with respect to H. And it will be the derivative of our loss function with respect to A times derivative of A with respect to H, but it's just derivative of sigmoid. And this is how we can write this in code. So in backward mode, we calculate the derivative only with respect to inputs. And the derivative of sigmoid will be just we derived this last time. It's just exponent over 1 plus exponent squared. Times the derivative from the derivative of our loss function with respect to H. Next and the last layer in neural network is linear layer. So linear layer has much more parameters. So linear layer has inputs. So we have inputs in our, so H is a linear layer. So the inputs are x's, and also there are parameters W and B. So we should calculate the derivatives with respect to inputs, for example. If you look at the first, on the first component of vector H with superscript 1, it will be this linear function. And this, so if you look at the second or the last component here, it will be the next linear function. But the good news is that the second line doesn't depend on the first row of matrix X. So only the first line depends on the first line from matrix X. So when we take the derivative with respect to the first, for example, element x1, 1, we should take the derivative only of the first line from our matrix H. And every H contains x1 with weight W1, 1. The next contains with weight W1, 2. Wait a second. W2, oh, sorry, W2, 1. And the last contains the weight in front of x1 with indices D1. In other words, the derivative with respect to x it's a little bit confusing here. In my diagram for neural network, my H was a column. So I use the column for H. In this case, H is a row. So, but the numbers W11, W1D, and so on, WD1, these numbers are actually the column of my matrix W1. So as the result, we'll get just matrix W1. Okay, this is the derivative with respect to input X. Derivative with respect to W. Derivative with respect to W. For example, with respect to W11. So every first component will contain W11. So it will be the derivative with respect to H1 times derivative of H1 with respect to W1, which is X. And so on times the derivative of the last vector H with respect to Hn, and derivative of this vector with respect to W11 will also give us the first component of vector Xn. And it will look like this. The derivative of our loss function with respect to matrix H, but transposed, because again, H is a column, but here it's a row, times X. And finally, the derivative of our linear layer with respect to bias term. The bias term is here, and derivative with respect to B will be just 1. So it will be the same shape, the same expression, but multiplied by the vector of 1s. So these are closed form solutions for derivatives, the same as we did for our computational graph. Like when you look at A plus B, we know the derivative with respect to A, it will be 1, and with respect to B, it will be 1. So the same is here, but the function is more involved. So the function is the entire layer of neural network, but still we have the closed form solutions for derivatives with respect to inputs. And this is how we can implement this in code. So in linear layer, we initialize randomly parameters W1, W and B. Then we calculate the H, the output, which is just W times X plus bias. And in the gradient, we perform two things. We calculate the gradient with respect to X, which was, as you remember, the loss times W. This is the out. But also, we update our parameters. So we calculate the gradient of our loss function with respect to B and W. As you remember, it was gradient transpose times X. This was gradient transpose times the matrix of ones. And then we update these parameters. So this is the formula for linear layer. Now let's apply this in code. So, okay. So this is our data. our data is just absolute value, and so I just initialize created array between x1 and 1 of x's, and y is just the absolute value of x. But then I also should reshape my x to get a two-dimensional array, because I want to use my functions, and the functions that I wrote, they were designed for input matrix X. And so on. So that's why when I create array of x's, it will be a one-dimensional array. So I just add extra dimension to get the shape of 50 times 1 instead of just 50 and comma. Because my functions I wrote functions that take the input two-dimensional array. Okay. So these are functions from the slides: loss, activation, and linear. And here is our model. So here's my model. I will apply to input x linearly, then activation. And here I indicate the dimension of hidden size. In this case, I am using 3, but you can use 10, and it doesn't matter. So this is DH. And then I go back from the hidden dimension to the output. So for example, if I apply the first layer, oh, it understands that I want to write. Model 0 is the first layer. If I apply this to my x, you remember my x is one-dimensional, 50 by 1. After applying the first layer, I will get 3 features for every point instead of 1 feature. Then I can apply, so this is h. Then I apply, for example, next activation. The dimension of activation will be exactly the same as the dimension of page. And then to the output from activation, I will apply the next linear layer, which is output. And what will be the dimension of the output? Do you remember? It should be just one number, because we approximate just a function of one variable. And after that, I can calculate the loss between O and Y. And I will get some number, which is MSE. MSE between prediction from our neural network and the target. After that, I should do the backward mode. So I should calculate the gradient of my loss function with respect to O. Then use this as input to the gradient of activation, and so on. And this is the final for loop. Um, well, I can actually show you. So if we calculate loss dot backward, so when I apply loss forward, it will memorize actually the O and Y. So in forward mode, it will memorize O and Y. So when I apply backward, I don't pass any arguments because the arguments are memorized in our class. So when I apply backward, it will calculate the gradients of my loss function with respect to O. Because O has dimensions 50 by 1, the gradient also has dimension 50 by 1. Then, so this is, for example, gradient with respect to O. Then I can, oh, okay, it suggests to write everything. So then we calculate gradient with respect to A, and it will be the backward of my second class in my list, which is activation, but I will use also inputs now. The inputs will be the gradients from the previous layer with respect to forward. You remember that in our functions, we calculate the gradients with respect to inputs and multiply by gradients with respect to outputs. So that's why we should pass the gradients from outputs. So okay, so when let's look at the shape. The shape should be exactly the same as the shape of X. But you remember when I apply backwards to my linear layer, inside this layer, we update the derivatives. So if I calculate loss function now, I believe I will get a different result. No, it's mhm. So when we apply, oh, okay, a big linear. Okay, I should apply backward, I believe, again. So, okay, yes, now the value is changed. If I apply it again, yeah, you can see that the value of loss function is changed because when I apply linear layer, every time I update also W and B. And ideally, the new value should be smaller than the previous one. And in fact, this value is smaller than the previous one. So the gradient descent rocks. Okay, now let's just write a for loop and apply this in for loop. So in for loop, I created array of loss where I memorize the loss. So let's plot the loss function. It doesn't, so it drops, but if I apply my model and plot the output from my model, this is the blue line. What do you think? Is it a good approximation? No, it's just approximation with average, with the average. It means that even though the loss dropped on the first iteration, is dropped drastically, we should still continue this gradient descent. So let's run this for 30,000 instead of 3,000. And now you can see another drop in loss function. And now I believe the output will be better. So from this example, you can see that gradient descent requires a lot of iteration steps. So next week, we also will cover other modifications of gradient descent that work much better and which are used in practice. But for now, we will use gradient descent. And in your homework, I asked you to apply this model for classification. If the decision boundary won't look great, it means that maybe you should continue training your model. You also can plot the loss function, and when you will see this abrupt drop, then you can stop your training, and the results should look good. So one tip for your homework, maybe instead of writing just for loop, you can create a class. A class, so this class will contain your model, your training loop. So here is the training loop fit. But the most important for prediction, it contains predict function. Because as you remember, there is a built-in this what's called the plot for decision boundary. So this function expects that the input algorithm has predict method. So here I wrote predict for regression. So predict is just applying my model to it. And then because it's two-dimensional, I remove one extra dimension. And then if you create a class, initialize this class, then you can train your model in a similar way, syntax like in scikit-learn. Just your model.fit. And yeah, and then you can increase number of epochs. Yeah, here is the drop, and then use predict to plot the prediction. Okay, so, and this is how we will later build neural networks with Torch. We will just import an M module from Torch and apply model.forward and model.backward. But this will be next week. So this week is still hard week. And then your homework, I asked to modify instead of MSE loss, you will use binary cross entropy loss because it will be classification problem. Okay. So now let's look at the computational graph, how it looks in, for example, torch. Now I hope you will understand this graph. So we have the graph for the function. So here's the function x times 1 times x2. Wait a second. I don't know what to say. I believe stands for activation, maybe. Then they take log, then sine of x2, then multiply log of this variable. It's a variable a. And sine of x2. So this is how they calculate the forward mode. They calculate f. But to calculate the gradients, we also should calculate the gradients of every node with respect to its inputs. So when you work with neural networks, they actually will store both. So the size will be twice greater than the size of the real number of parameters, because it will also store the gradients with respect to inputs for every node. Okay, finally, why we will use PyTorch and not TensorFlow, or who knows, another most very popular framework for neural networks, which works with CPUs. And for some reason, in this list from NVIDIA, there is no this framework, but this is a very popular framework from Google, which allows to work with Google CPUs. Multidimensional arrays they call tensors, and TPU stands for tensor processing unit, like graphical processing units. It's called YAX. Maybe I spelled incorrectly. CPU. Oh my gosh. I can't find this. Look, it's called YAX. Oh, JAX. Okay, so this is the JAX. Okay. So this is the if you want to work with Google TPUs, and only Google have these processors because of what's called patents restrictions. They can't sell this, but they can run your code on their TPUs. So they work with JAX language. The popular language framework is TensorFlow from Google, but later it became less popular, and PyTorch is now the mainstream, and maybe that's why they created another like reincarnation of TensorFlow, which is JAX, to make it again popular, because you can't use other frameworks with CPUs, so you should learn JAX for that. There are other frameworks which were used, but now they're not popular anymore, like Piano and so on. So why will we use PyTorch? I kind of mentioned that it's now mainstream in at least in research. In production, TensorFlow maybe is used frequently because historically TensorFlow has implementation of JavaScript support for mobile development, so that's why it worked from the box. But now Torch also has the support for JavaScript. And I just Googled some opinions about which framework is more popular, and I like this one. The only reason to use TensorFlow instead of PyTorch is if you are forced to do so. So we will use PyTorch because we are not forced to do TensorFlow. But again, the differences are very minor. If you learn one framework, you will easily work with another framework. It's kind of Python and NumPy, so very similar. Okay, so we will use the PyTorch installed on Google Colab. But if you want to install this on your machine locally, you should go to PyTorch work page, and it will suggest the version specific for your device, because you can have different CPUs, different generations of CPUs, different Python versions, and if you install a little bit different set of parameters, it just will give you an error when you will run it. So, but it's pretty simple because it will detect the configuration automatically. Okay, that's it for today, and yeah, next week we will start begin working with PyTorch and implement neural networks with built-in libraries instead of hand crafting them.